I'm Hyuk-Jin Won, and I'm software engineer at Databricks. So today I'm gonna talk about Pandas UDF and the Python type hints here. So Pandas is probably one of the most commonly used the Python library or tools in data science. So a few years ago, the Pandas UDFs were introduced to improve the performance usability. Users could use Pandas APIs directly in the UDF, and then it solved lots of problems in the regular Python UDFs and the Python RDD APIs in PySpark. And after a couple of years, we started to face some problems and confusions as it rapidly grows. So, um, and at the same time, there has been a kind of a trend in Python about the type hinting in general. So it provides a better static analysis with a lots of benefits, and but it's kind of still premature, but it's encouraged in general. So this talk will cover how Python type hints solve the problem in the all Pandas UDFs, and then also introduce new Pandas APIs in Apache Spark 3.0. Yeah, so I'm one of the Apache Spark committer, PMCs, and I'm software engineer at Databricks. And I'm one of the major contributor in Koalas, which is Databricks project I'm working on. And I'm pretty active in GitHub, in particular the Apache Spark repo. Yeah, so today this is my agenda. So I'm gonna first talk about what are the Pandas UDFs and Python type hints, and then the problems in the all Pandas UDFs. And then I'll talk about how I solve this problem by using Python type hints in Spark. And lastly, I'll introduce the new Pandas APIs with Python type hints. So first of all, to just give you a bit of backgrounds, I'll go through the Pandas UDFs and then how it works first. So in general, Pandas UDFs or like regular Python UDFs or Python RDD APIs serialize the data and function from JVM to Python. So in Pandas UDF specifically, it uses Apache Arrow with almost zero cost when they serialize and deserialize. And also Pandas UDFs can perform the vectorized operations in serialization, which improve the performance hugely. In addition, they allow you to use the set of rich APIs in Pandas and NumPy. So here is an actual example. So as you can see, it adds 1 to each value. So it's wrapped by Pandas UDF decorator. And then the UDF evaluation type is specified as Scala. So it's a Scala Pandas UDF. Inside the function, it adds 1 and it's vectorized. So it takes more than CPU design into account, such as SIMD or pipelining. On the right side, this is how the function actually applied against the actual data. So the black color is kind of the logical representation of a Spark data frame. So it has columns, and then the column has values. Physically, they're distributed, but logically, they're one data frame. And the red color represents the physical unit that the function actually takes as input and output, which are Pandas series. So I'll talk a little bit more about the internal and how it works. So let's suppose we have Spark cluster. So we have the 3 workers, and then the master and drivers are not shown for simplicity here. So usually Python workers are not created when it does not use Python native functions. Only when the Python related operation happens, then it lazily creates the Python process to interact with them. So once you create a Spark data frame and then performs an operation, this is how actually it looks like. So it loads partitions into workers and then start to process. So when they have to execute the Python functions for Pandas UDFs, it serializes and then send the data from JVM to Python processes. So each partition becomes multiple arrow batches and then transferred to the Python processes. Each arrow batch is converted to Pandas series, and then the user functions are executed finally together. So the function pandas plus one takes the pandas series and it adds one in vectorized manner by leveraging the pandas and numpy, and then it returns the output series. After that, the result of the user functions are converted back to arrow batch, and then they become the Spark partition map. So here's the performance results between the regular Python UDFs and Pandas UDFs. So as you can see in the Pandas UDFs, there's a huge performance improvement when you compare it to regular Python UDFs. So this is how the Pandas UDF works in general. And then before we talk about more how Pandas UDF and the Python types teams work together, I'll briefly talk about what are the Python typings first. So the Python type hinting is basically a way to express which types are expected for variable or functions input or output. So the typical Python codes, like the first example, don't have the types. So because of the nature of the doc typing in general. So usually you don't know which types are expected before you actually execute the functions or read the documentation. And then the second example shows the Python type hints. So unlike the typical Python codes, they are all, completely optional, and you can easily tell which types are expected for the input and output. The Python type hinting was introduced from Python 3. So this is the standard way of notating the types. And you can use it for, like, for instance, better static analysis or possibly runtime checking or code generation potentially. One of the benefits of the Python type hints is IDE support. So this is my PyCharm, and when the function specify the Python type hints correctly, and then users can see the warnings when they call it with a different type. So for example, there's an API here called merge. And then when I use the string for the second argument, that should be a data frame, it shows warning because the type is not matched. So developers can easily avoid such simple but very common mistakes. So another benefit is the better static analysis and auto documentation. So I use MyPy in the project that I'm working on. The warnings you've seen in the IDE can be actually actual errors from the static analysis. So again, it makes you avoid such basic mistake automatically. And it is not possible in the regular Python codes without type hinting. So this is one of the benefit. And then another one is that it also can automatically document your codes. So you don't have to list up the which types are expected for the input and output because they are automatically documented. The second example is that the Spinkis generates the documents for the types. So Python type hinting is still kind of premature, but it is in general encouraged because of many benefits. There are so many tries out there. For instance, like Pandas itself has a Python, trying to have Python type hints. And PySpark itself has the type hinting support, although it's currently a third-party library at this moment. Right. So now we know what Pandas UDFs and then Python type hints. So I'm going to talk about what kind of problems we actually faced in the Pandas UDFs, and then why we had to redesign Pandas UDFs here. In Spark 2.4, we have three kind of Pandas UDFs. So the first one is the Scala Pandas UDF. It just transforms the values from A to B using Pandas APIs. The second one is the GroupMap Pandas UDF, which splits the data to each group by the given function, and then applies the function and then combines back to a regular Spark data frame. The last one is the group aggregate Pandas UDF. And it does exactly the same thing with the group map Pandas UDF, but it requires to aggregate each group to single Scala value. Actually, the return value from three Pandas UDFs are different for each type of Pandas UDF. In case of Scala and group aggregate, it returns a regular Spark column. That is actually the same with the other Spark columns. So you can operate or perform with the other Spark columns or expressions. However, the group map Pandas UDF returns a Spark data frame. So there's difference here. So I'll talk about this a bit more later. In Spark 3.0, there are even more new types of Pandas UDFs implemented. So the first one is the Scala iterator Pandas UDF, which allows you to use an iterator within the Pandas UDF. Then the second one is the map Pandas UDF. This also allows you to use an iterator, but it's more like a map partitions in RDD APIs. And the last one is GroupMap Pandas UDF. This is similar with the GroupMap Pandas UDF, but it allows you to co-group in two different data frames. And in this case, the Scala iterate Pandas UDF returns a Spark column, and then the other returns a Spark data frame. So, here's the complexity and computance. So the first problem is that the increasing number of Pandas UDF started to make confusions to users. For example, the three Pandas UDFs here above all measure the same. But the type of the Pandas UDF is different, and then the input-output for the functions are also different. And it's difficult to tell what are expected. The first Scala UDF takes and outputs a Pandas series, and then the second one requires an iterator of series. The last one expects a data frame for its input and output. So it's difficult to tell what types are expected in the function. It's not very clear how each UDF works, and then why we should specify each UDF type. And then here's the second problem. So the first example uses the Scala Pandas UDF, and it adds cosine to the results by using Spark expressions. So as you can see, it works fine. But the second example uses GroupMap Pandas UDF, and there's no way to directly add the cosine. This is because the first example of the Pandas UDF return a Spark column instances that can be mixed with other expressions or like functions. However, the second Pandas UDF return a Spark data frame instance. So some of the Pandas UDFs return a Spark column, but some of them return a Spark data frame. Internally, the first example creates an expression, but the second example creates a query execution plan. So both are technically separate concepts, but they are currently in the same category as the Pandas UDF. So Spark community had to discuss a lot to address the problems. And then finally, we kind of made it. So now, finally, I'm going to talk about, I'm going to introduce the new Pandas APIs with Python typings. So we came up with the two main points to think for redesign. So the first is the Python typings. In Pandas UDF context, there are three advantages. Firstly, it's self-descriptive. So the user-defined function describes itself and knows what to expect for input and output. It's very easy to tell what function is supposed to do. Then the second thing is the static analysis. As I said, the IDE supports Python type hints, and then the other tools like MyPy can detect the common mistakes about the typing the Python developers usually make. And lastly, it automatically documents your Pandas UDFs. So you don't have to bother document which argument should be which type in the documentation. So by using Python type hints, the UDFs can be simplified like the left side. And then the second point is the API separation. So some Pandas UDFs return a Spark column, but the others return Spark data frame. So they're now separate. So the former stays as a Pandas UDF as is, and it still returns a Spark column and can be mixed with other expression or functions. But later became a separate API group called Pandas Function API. So they work like an API in data frame in general as query execution plan that holds expressions internally. So now I'm going to introduce the new Pandas UDFs one by one. So the first is service to service Pandas UDF. Previously, it was called the Scala Pandas UDF, but now it's called service to service Pandas UDF. So in the new style, you don't have to specify the Pandas UDF type, but only the function itself describes the input and output itself. The second one is the iterator Pandas UDFs. So this is a new Pandas UDF introduced in Spark 3.0. So this can be used in both old and new styles because the old style isn't deprecated for now. And then the function expects an iterator of series, and the total length of the output and input should be same. This is also iterator support in Pandas UDF, but the input side, it takes a tuple of series in the iterator. So the all characteristics are same with the other iterator support, like the length of total input and output should be same, and then the struct type is represented as a Pandas data frame. These two iterators supporting the Pandas UDFs are actually pretty useful, especially when you have an expensive computation to have one state to share. The example on the left side computes an expensive initialization and then use it for the whole iterator process. So this could be a common case in machine learning when you, for instance, load some model. Another example is that when you prefetch, for example, you can consume the input iterator in a different thread to save IO weights, and then computes the output in the main thread. And it could improve the performance of your Pandas UDF. The last one is the series to Scala Pandas UDF. This way was previously the grouped aggregate Pandas UDF. So it expects a series to be aggregated to a Scala value. The Scala value should be a Python primitive type or NumPy data types. The old style of usage on the right side can be converted back to the new style on the left side. And this is the new category introduced from Apache Spark 3.0. So the Pandas Function APIs create a query execution internally. And Pandas UDFs create the expressions. Well, at this moment, the Python type hints in Pandas Functions APIs are completely optional. So you can omit the Python type hints, but it's encouraged to use Python type hints. So this is the first one, and then this is the GroupMap Pandas Functions API. It was previously GroupMap Pandas UDF. So it splits each group by the given condition, and it applies the function, and then combine back to the Spark data frame. The function expects a Pandas data frames as input and output. The second one is map Pandas functions. This is also introduced in Apache Spark 3.0. This is similar with map partitions in RDD APIs. So you can transform your Spark data frame by using Pandas data frame. It shares the same characteristics with iterative version of Pandas UDFs, but one difference is that it doesn't have the length limitation. So you can return the arbitrary length of the output. Lastly, co-grouped map Pandas UDF function. Lastly, co-group map Pandas Function API. So this works similarly with the group map Pandas Function API, but it can perform with the two different data frames. So for instance, if you have two data frames and then say they're grouped by the same condition, then you can actually do like something like as of join or things like that. And then you can combine to single data frame. So it's pretty useful. Okay, so to recap, the Pandas APIs now leverage Python type hints with many benefits, such as static analysis, auto documentation, and self-descriptive UDFs. The old Pandas UDFs become a separate groups into Pandas UDF and then Pandas Function API. And the supports of the iterator and then core group map and the map transformations are available in Spark 3.0. Yeah, so that's it for now. Let me know if you guys have any questions.